Hello, hello, hello. Hey everyone, how are you doing? Good. I'll try not to scream and deafen everybody here. So, hey everyone, thanks a lot for coming out today. My name is Dan Ayub. I'm executive producer of publishing at 343. Presenting with me today is the lovely and talented Greg Herman, who will be coming up on stage in a little while, who is our technical director at 343. So, and we're going to talk to you today about Halo Spartan Assault and what the process was of bringing that game to life, making it live on mobile platforms, making it live on Windows platforms. Of course, this was a game that existed in a very different space. It was a first-person shooter on a console. So we had a lot of fun and we had a lot of challenges in the course of this development. We're going to share some of that with you guys today. Quick bit of background for people who might not be familiar with 343, who we are, what we do. We are a division within Microsoft, and our mandate is management of the Halo franchise. It's as simple as that. So anything that touches the Halo franchise is run through our group. So consumer products, books, web series, and of course games. All of those sit under our franchise. All of those sit under our roof, and that is our sole purpose for being. So a little bit about myself. Again, my name is Dan Ayub. I've been in the games industry for about 15 years. And I worked at a lot of different companies and made a lot of different types of games in my time. Worked at Ubisoft, Electronic Arts, Disney. And during the course of my time, I've done pretty much every genre you can imagine on a bunch of different kinds of platforms. Obviously console, but also PC, handheld, things like that. But I'd never actually done a mobile game prior to starting to work on Halo Spartan Assault. And this was interesting to me for a number of reasons. First of all, as you guys know, it's always great when you can flex a new muscle. We're all in this for the same reason, because we want to learn. We constantly want to be pushing things forward. So it was very interesting to me for that standpoint, because it was an experience I hadn't had before. The other thing that was a fascinating attraction for me was it presented a really interesting challenge. Again, Halo had always existed under a different set of circumstances, and our challenge was now to take this gameplay that people have known for over a decade, and is one of Microsoft's largest game IPs, and make it work on a very different set of devices. So that was a challenge that was really inspiring for us, a challenge that was really, really exciting. We learned a tremendous amount, and we're going to share some of that with you guys today. So just quickly, what are we going to talk through today? First of all, the decision to take Halo to mobile, why we did it, what we were thinking, and just as important, what we didn't want to do when we made this decision, because there was some very, very important things we wanted to stay away from. The process of converting Halo to mobile, what did we think about, what did we do, where did we go right, where did we go wrong? There's a bunch of different things that this process really brought to light for us, and we'll have a fun discussion around that. And finally, the design and development challenges that came as a result of that. At that point, you'll get rid of me, and Greg will come up and speak a bit about the technical challenges, the key technical learnings we had, and he'll also talk about some of the tools that we have available to us, that obviously you have available to you guys as well, that you can really use to help make a fantastic experience on Windows devices. So I realize everyone may not be familiar with Spartan Assault, everyone may not have seen it, so just so we're all kind of working off of the same basis, I brought a quick video. We prepared this for E3, where we were on the floor last week, and this will give you a quick idea of what the game is, what it looks like, all of that good stuff. You have to audio? Thank you. So obviously it was a tremendous amount of fun for us. So at a high level, what is Spartan Assault? As you can see from the video, it's a twin-stick action arcade shooter. That was really the type of game we wanted to go for. Think Robotron, think Smash TV. These were games that really inspired us throughout the course of our development. That twin-stick, fast and furious kind of action where something is always going on. Now, obviously, that's very different from the primary Halo experience that people are used to. So how did we get there? How did we get to this experience? So we had a couple of pillars in mind when we started the course of the development. The first goal we really had was how do you untether the Halo experience, right? So up until this point, if you were playing Halo, you were sitting on your couch, you were sitting on your chair, and you're playing, in front of your television set. How do you take that experience, something that's been designed so specifically for one interface, and you make it work in a completely different world? This is what we came to. This is where we had to get new ways to play. This is why the gameplay experience that we're going to show you today is so different from the core gameplay experience that people are used to. Other thing we wanted to make sure we did was innovate on the platform. Halo has always existed for, obviously for a number of reasons, but one of them is to push the platform, push what's possible, and just kind of be this crown jewel that people can look to when they think of the Xbox platform. How do we take that and we do the same thing on Windows devices? We wanted people to look at this game and just say, man, how did they do that? They've got cinematics. Look at all the action that's going on at the same time. Look at how much power they're pushing. We wanted to set a very high bar for gaming and invite other people to topple it, invite other people to go ahead of that bar, because you have tremendous power at your fingertips with these types of devices. And mobile gaming, when people generally think of mobile gaming, they think of limitations. And we wanted to break that paradigm and show that you can be just as creative, just as dynamic, and you can do some amazing things on these types of platforms. The final thing, and this was really, really personally important to me and to everybody on the development team, was the right game for the right screen. Now, obviously, we're not the first large IP that's made the move to these types of platforms. What we did not want to do was just port our console experience and bring it over, right? Because obviously, we created experience around a controller, around a TV that was made exactly for that interface. So we did not just want to take that and smash it on a tablet and PC and mobile and hope for the best. We had to create something very, very different. So what was that process? So getting started, obviously very high expectations, right? It's Halo. Halo brings with it a lot of expectations. When people think of Halo, they think of the sandbox where you have multiple ways to accomplish your mission. They think of jumping into any vehicle throughout the course of the game, picking up any weapon, beautiful vistas, gorgeous art, a compelling story, great audio. All of these things are really core to what the franchise is. So that had to exist on the new platform. And that was a really, really important point for us is, if you're transferring things over from one platform to the other, you still have to maintain the soul of your product. And that's something we were very, very adamant about. The second thing that was really important for us in this process, that we had to make a great game first. Now, we wanted it to be as similar as possible, but as a general rule of thumb, when we got to a breaking point, fun always won. So when we did have to say, yeah, this really isn't how this vehicle would behave in the game or something like that, that was okay, because we wanted to keep our customer in mind and we had to keep our platform in mind. So our challenge really became, when people think of Halo, this is what they think of. So how do you take that and make that work onto very different types of screens? So controls is the big one. Obviously, twin stick, that's not the control scheme that's normally associated with Halo. I said very often that we were going to live or die based on our ability to make the controls work. So if anyone here has ever played any kind of twin stick shooter on mobile or any kind of mobile game in general, you run into a few problems, and controls is generally the first thing you're faced with. One is the glide issue, right? You guys have probably all experienced this when you're playing and your hands start moving and you're constantly resetting and things like that. That's a tremendous problem that we wanted to get around. And actually, the interesting thing we did, the way we went about that, was we designed an adaptive control system that we just assume it's going to happen, right? People's hands are going to glide, so don't try and change how your user is going to behave. Try and change how you can change your own approach, so you're taking that into consideration. So we just accepted that the user's hand is going to glide, so we created an adaptive system, and I'll show it to you in the demo in a couple of minutes, where when your hands do glide, your controls move with you. So it sounds a little wonky, but it is actually a tremendous amount of fun. Wherever your hands end up, you still have control. You're not constantly resetting your balance. And what we usually see with this control system is within 2 to 3 minutes, people are just in there and going, which is fantastic. I can also tell you, we probably changed our control system more than 15 times throughout the course of our development. So be prepared to iterate when you're doing this kind of thing, because as we found, our first guess was often not the right one. Now, the second one was consumables, right? That's something that's very familiar to mobile users and something we wanted to make sure that we were giving people, but not something that's generally associated with what we do in Halo. So we wanted to make sure we didn't break things, so we created a system whereby, you know, as you're playing, your classic thing, you're playing, you're accruing points, you can use those points to buy new abilities, buy new weapon types, buy new armor abilities, and bring those into the game with you. And of course, you know, for the person that doesn't want to grind their way through it, they can also, you know, just purchase points and use those to buy things. The other thing we wanted to do was take in mind how the player plays, right? So your console user behavior is very different than your mobile user behavior. So we didn't want to design an experience where we were forcing a player to sit down and crank through for like 3 hours in one shot. So what we did, I'll show you the interface again in a couple of minutes, we actually broke it up into digestible chunks. So if you're to play the entire game from start to finish, you're probably looking at about 2.5 hours. But we broke them up into like 4 to 5 minute chapters. So if you do have just a couple of minutes, you're waiting in line or for something like that, you can get in there, you can hop in, and you can go right away. And the other thing, going back to what I said a little bit earlier, was that innovation on the platform. How do we make people, with this game, really see what the platform is capable of and just be blown away? And you know, I think you're going to be pretty happy, if you haven't seen the game yet when we go through it in a little while, to just like see what we're able to do on these devices. It's really, really quite impressive. So let's get to it. And of course, I went into power save. And see if I get this right. Yes, we did. Okay. So I will attempt to play with all these cords hanging out here. So I'm just going to hop into this one, and we'll show the controls really quickly for what I was talking about. So wherever I put my hands down, you're going to see my reference point form, which is a lot of fun. So players kind of put their hands wherever. So this, you know, very simple. This is your movement. The right side is your shooting. But what's fun is imagine a world where my hands start gliding. You can see how that's moving with me, and I'm never actually losing my control input. Now, the other thing we wanted to give the player was the options for choice. So we obviously designed with touch in mind. You can also play with a mouse and keyboard. And shortly after release, we're going to support controllers. So you can plug in an Xbox controller and play that way. So we give the player a bunch of different choices. So can we get audio on this? Other than that, I'm going to start making bullet sounds myself, and you guys are going to find that much less cool. Okay, I'm just going to go, and we'll hopefully get some audio coming out of this at some point. And we'll give you guys a chance to play this a little bit after if you want to come up. So immediately, I mean, what we wanted to do was push that feel. I mean, you look at the graphics, you see what it's capable of. We've got the shadows, we've got a bunch of different things. And, you know, these presented obviously some interesting design challenges to us and some big technical challenges for us as well. And Greg, when he comes up in a couple of minutes, is just going to talk about some of the things we did, some of the tools we have at our availability that is actually going to make these things a little easier for you to do, and some great things you've got to take advantage of to really optimize your development. This is actually a great point. I love this spot because you can just see how much action is going on at the same time. And you know, the other thing I should note is that this is the same experience that you're going to get on the phone. So whether you're playing on the phone, I'm playing on the tablet just for the ease of simplicity with all the cords and everything coming out of it. But this is the same thing. This is a AAA experience that you've got going on right at your fingertips. Woo. And you know what? That's okay. And that represents some pretty exciting things, right? I think it represents some pretty exciting things to us as developers, because we now have some pretty awesome things at our disposal to give to people and really change the implications of what you can do with a gaming device. So I'm just going to hop out of this really quickly, and I'll jump into a different mission just so you can see a bit of the variety that we have in the game. Oh. Sorry guys, just bear with me here. So this is obviously the risk of live code. All right, here we go. So you hop back in. I'll just show you an example of one of our intro missions right off the bat. You can see a very different style of gameplay. So of course, similar to Halo, right? You can choose your loadouts. You can choose your skulls. We're going to have a variety of things available to the player to bring them back. So daily challenges, which is going to encourage the player to come back that are specific to missions. We're also going to have weekly challenges. And just some of the things we've done, right? When we really wanted to, again, push the innovation level. You're always going to have this notion, you can see the ships landing in the background, that you're part of a much larger battle. And I really apologize that we don't have audio for you guys because the audio is pretty amazing. We did a bunch of things you don't normally see on this kind of platform. We did 60 minutes of original audio specifically for this game. We are pushing a story. We've got cinematics in this game that are going to help push things forward, and we've connected everything we do, as we often do, to that larger Halo franchise. So it was really important for us in the course of our development just to make sure that whatever we do, it still feels like the player's connected to that larger experience. So that's it at a very high level. These are what we wanted to accomplish from a design standpoint. These were the principles we went into it with. Very excited. We're coming out in July. Things are moving along nicely. The game's in great shape. We had tremendous response at E3, which is great. But of course, it all comes down to execution, right? So we had all of these things we wanted to do, but this created a pretty interesting technical challenge for us as well. Luckily, I have access to somebody much smarter than me, with Greg, who was able to work with our partners to solve all of these technical problems. So I'm going to invite Greg up on stage, and he's going to talk a little bit about some of the techniques we used and some of the tools at our disposal. Greg?
Excellent. My name is Greg Herman. I'm a technical director for 343 Publishing. I've been with Microsoft for about 15 years now, in games for 10, and working on Halo for the past 5. I'm here to talk a little bit about the nuts and bolts of how Halo's been built over the past decade, how Halo Spartan Assault is put together, and some interesting things we found along the way. A few important notes. The primary developer of Halo Spartan Assault is Vanguard Games, but they do let me and my team contribute from time to time. There's a little bit of echo. Okay. And I'm also going to compare a few apples and oranges in areas where there is no absolutely right answer. There may even be a few outright lies. I might even use the term Xbox One to refer to the original Xbox, but don't hold it against me. It's in the interest of time. So let's take a bit of a walk through memory lane and see how we're re-evolving the franchise to tablet and mobile. So back in November of 2001, Microsoft launched their first console. Taking many components from off-the-shelf PC parts, it featured a low-end, but still pretty capable Intel processor. 64 meg of memory was also not too bad for the time, but the real standout was the GPU. Co-developed by Microsoft and NVIDIA, it could output nearly a gigapixel a second. Last, most televisions were just standard definition, 640 by 480. Bungie and Microsoft released Halo 1 with the console, clearly defining what first-person shooter meant for console gameplay. Halo 2 followed in 2004, building on a wave of new features from Xbox Live and really setting the standard for console internet multiplayer. In November 2005, Microsoft launched their second console, the Xbox 360. It was a significant deviation from the original Xbox. Microsoft's console was now a lot closer to its contemporaries, with a triple-core in-order processor at a fairly substantial clock rate. The in-order nature made it somewhat less friendly to heavily object-oriented code, so much so that naive single-threaded ports would often run slower than they did on the original Xbox console. It took a while to redesign our code to get the most out of the system. Even in 2012, titles like Halo 4 are still setting new visual standards. The 512 meg of unified memory came as a surprise to many who were expecting just 256, but that 512 has been a large factor in the overall longevity of the platform. And while the Xbox 360 GPU is only clocked at roughly twice the rate of the original Xbox GPU, the total ALU throughput is significantly greater, much closer to 10 times the original Xbox performance. And with the new console, high definition, 1280 by 720, became our new resolution target. On Xbox 360, the Halo franchise really exploded. We shipped 6 full-box titles, the Halo Waypoint console service, and companion experiences for Windows Phone, Android, and iOS. It was also the first time we moved the franchise beyond FPS with Halo Wars. Now, in October of 2012, Microsoft released Surface RT. Spartan Assault development was well underway at the time, but once RT launched, it quickly became our target platform. The Surface RT is a quad-core machine not specifically targeted at gaming. The ARM A9 processor is out of order, allowing it to run general-purpose code fairly efficiently. The 2 gigabyte memory is great to have, but it is single-channel and shared with a substantial OS, so we do need to temper our expectation on how much we'll try to use. The GPU is 300 megahertz NVIDIA ULP ultra-low power, with an ALU performance of only around 7.2 gigaflops. And the native resolution for the tablet is 1366 by 768, greater than the 1280 by 720 resolutions we've traditionally targeted on console. So here they all are side by side. As we move forward in time, our target platform CPU performance has generally continued to improve. With multi-core, we're at a point when dedicated update and render threads are absolutely the right call. Memory has also significantly grown, though it's still a challenge to design for both the tablet and the mobile platforms, some of the mobile limits being on the order of 100 to 200 meg. Our target resolutions have continued to increase, moving from about 300,000 pixels on the original Xbox to just under 1 million on Xbox 360 to substantially over 1 million on Surface RT. And our GPU power. Well, that's where things get a little interesting. While I do quote 20 gigaflops for the Xbox, or for the original Xbox performance, it had a very limited fixed function pixel shader, and the 20 is really a peak possible performance number. Even so, the effective Surface RT's GPU performance is at or near Xbox One, and still an order of magnitude away from Xbox 360. So what's a big trade-off? Well, it's power, really. It's all about power. Surface RT performance per watt is by far the clear winner among all three. The 10-watt number itself, quoted, is really only a very rough ballpark due to the aggressive way the operating system downclocks to conserve power use. In practice, it typically does much better. So, we do need to rethink a few things. Compared to current consoles, CPU speeds, accounting for multi-core, are relatively in the ballpark for general-purpose code. Memory's okay, but we really can't rely on raw GPU performance. So what do we need to rethink? Well, with our form factor changes, we definitely need to look at gameplay, as Dan mentioned. Lighting, models, materials, environments are all very GPU intensive, so we will need to rethink our approaches to those also. Physics, animation, and audio are traditionally CPU-heavy tasks, however. And because of that, we can often continue to rely on the middleware and techniques we use on Xbox 360 today. For example, Halo Anniversary and Halo Spartan Assault are both using the Fmod middleware for audio playback. Spartan Assault is also able to use additional cores for animation, static geometry processing, and scene graph updates. So we're definitely very heavily using multi-core for these devices. For the areas we do need to revisit, primarily gameplay and graphics, let's take a bit of a closer look. As I noted earlier, and Dan noted, the name Halo is synonymous with first-person shooter gaming. Its close-up action, visceral feel, and expansive worlds have really been a hallmark of what the Halo brand is. But would that game style translate to a primarily touch-based experience? A few years ago, when we were making Halo Anniversary, we were actually spending a lot of time with the Halo 1 codebase. The natural question was raised by management whether we could just port Halo 1 to mobile and tablet and just kind of do it that way. We actually did. We formed a small team. We built a prototype of it. But in short, the answer is not really. Touch input is very well suited to many different styles of games, even some FPS games. But we found we really couldn't do justice to the Halo brand and build in the same quality of twitch action and tight controls into FPS. So clearly, we need to do something a bit different. And Spartan Assault. So Spartan Assault pulls the camera out the third person and moves to that twin-stick shooter control scheme. This helps us in a number of different ways, but first and foremost, the twin-stick input works very naturally with how users interact on tablets and mobile devices. It was extraordinarily important for our gameplay to just not feel forced. Also, by fixing the camera angle, we reduce Halo first-person shooter use of 8 buttons, 2 analog triggers, a D-pad, and 2 thumbsticks, down to just thumbstick-style input and relatively few UI elements. We built the environments as multi-layered. In many of the levels, you can see battles ongoing in non-playable areas, creating the perception of being involved in large-scale conflict while still allowing the game to very tightly control object counts. Spartan Assault also brings over much of Halo's sandbox feel, having a large variety of weapons and vehicles. However, Spartan Assault recognizes that it's an arcade experience first and foremost. So whenever choices had to be made on whether something would be like the FPS or fun, we always chose fun. So let's talk about how our visuals support those gameplay choices. Halo has always incorporated state-of-the-art global illumination techniques. Back on the original Xbox, Halo was using a bespoke photon mapper and using those results to light their environments, objects, and particles. Pictured here is an example of the light map for Halo 2's Zanzibar multiplayer level. The entire pipeline was also low dynamic range only. Some nods were made towards gamma correction, but having a fully gamma correct pipeline was not really possible. Halo 2 also used stencil shadows, a technique heavy on fill rate, but relatively low memory impact. But on Xbox 360, things got quite a lot more complicated. Now, instead of just storing a simple color for light maps, Halo 3 stored a spherical harmonic encoding of the three-dimensional lighting environment on a per-texel basis. Think of it like using a relatively few parameters to describe how light is incoming from all directions simultaneously. In order to reduce texture memory usage, those parameters were converted to a different color space and encoded into compressed textures. To accurately reconstruct a lighting environment, Halo 3 samples from 10 different light map textures. Pictured above is the encoded compressed light map for the Halo 3 multiplayer map Last Resort, a direct remake of Zanzibar from Halo 2. The overall pipeline was updated to be fully gamma correct and to incorporate high dynamic range. Motion blur, anti-aliasing, and other full-screen post-processing techniques were also included. And photorealism is a pretty complicated science. So with Spartan Assault, with the GPU restrictions of our low-powered platform, we really need to fall back to our older techniques. Our light maps are, again, a single color radiance, and our objects now sample their lighting environment from a single globally defined cube map. Spartan Assault is LDR only, but DX11 does help us be gamma correct by clearly defining how sRGB to linear conversions occur. Our shadows are simple blobs, neither having the fill rate to do stencil shadows, nor being able to efficiently use render target-based techniques like shadow mapping. Now here's an example of the Spartan model from the original Xbox. This is the mid-range LOD from Halo 2's multiplayer model. Note the lack of articulation of the fingers and relatively low overall polygon count. Halo 2 featured diffuse and bump maps, and the overall material model was roughly Blinn-Phong, a computationally efficient model that mostly just looks at dot products between normals and a given lighting environment. And here's the associated shader microcode. Please note, there's no real microcode from the original Xbox. This was taken from our Halo 2 PC port. This is one of those lies I talked about at the beginning. It's pretty efficient, though, with just about 24 ALU operations and 3 texture lookups. Now, on the 360, things got more complicated. Our meshes became more than 5 times more dense and now incorporate information from diffuse and normal maps along with cube maps along metallic surfaces to reflect their overall environment. There was a very strong desire in Halo 3 to approximate the Cook-Torrance lighting model. While the Blinn-Phong model we discussed earlier is highly efficient, it tends to look artificial. Cook-Torrance is more physically based and far better at representing a wider range of materials, in particular metals. And here's the associated shader microcode. Our shaders grew far more complicated. We now have 5 times the texture lookups and nearly 10 times the ALU operation, along with large swaths of conditionally executed code. Note the ellipses at the end of the page. It keeps going. Okay, and here's our Spartan Assault models. They're built very close to the budget of Halo 1's models and use a much more efficient material model. Note the textures for the character were built to improve visibility for the third-person camera and not for photorealism. And here's the shader microcode. The 3 texture lookups and 17 ALU operations are very comparable to our original Xbox shaders. So, what did we learn? Fun trumps all. There are high-quality ways for you to bring your franchise to tablets and mobile without trying to force the control style of a direct port or rebuilding all of your asset libraries. Go back to your old bag of tricks. Many of your original Xbox-era techniques will scale quite well, and you can even mix in some modern global illumination effects. With the CPU power of these platforms, you can mostly continue to use the middleware you're already familiar with. Spartan Assault's using Fmod for audio, Beast for lighting, Bullet for physics, Scaleform for UI. You should still expect to rein in your overall object counts a bit. With the GPU, you definitely need to be pretty careful. You're going to want to limit overdraw, manage expectations around photorealism, material model, and render target use. I would definitely look towards your original Xbox-era budgets. Now, that said, it was just 4 years between the original Xbox and the Xbox 360. I'm expecting and definitely hoping to see similar strides in the mobile and tablet space over the next 4 years. And last, the Windows Store titles give developers a whole lot of choice, really. You can choose to build in JavaScript, HTML, or manage code in XAML, or native code in XAML for that matter. But for highly efficient games, they also allow you to simplify down to just straight native code with no XAML overhead using just core window like we did for Spartan Assault. If you really do limit what you require from the OS to kind of its most basic level, you can definitely get the most out of the hardware and kind of limit surprises. And there were definitely some surprises, however. So I'd love to go over a few of those with you and to show how we use just all the different tools that Microsoft has and provides to be able to identify and resolve them. So just give me 1 second here to switch over. We were on 6. Excellent. So the first thing I'm going to look at is just a very straightforward Visual Studio performance analysis. You can just capture this directly from the menu, and it works great for Surface RT and pretty much all of our platforms. Okay. So you can typically approach kind of performance analysis 2 different ways. In particular, in publishing, we tend to spend a lot of time just focusing on perf. But usually you can start working top-down and try to figure out whether the different particular areas of your code are taking the amount of time you expect, or you can kind of look bottom up, which is to say, okay, what are my highest exclusive time functions, and why are they so high relative to those other functions? So we'll look bottom up. We're not going to use symbols for the game code today in deference to our partners' intellectual property, but we can definitely look at what they're calling from the OS. Are you guys able to see this okay, or do you need to zoom? Okay, well, we'll see if we can zoom a little bit. That's not going to work. Let's get rid of view. Okay. So in this case, we're going to be sorted by exclusive samples, and we're just going to look at just let's redo this a little bit so you can get a little bit more of this in. Exclusive samples by percentage, and we'll just look through a few different functions. Usually, you'll see something like malloc-free. Memory allocations tend to usually bubble up to the top in some of our reports, so we did have some work to do there. One of the ones that really kind of stood out to us on this one was really this get native orientation function call. So let's look at that a little bit more. So that's called directly by the game, and that actually maps to the OS display properties get native orientation call. It's just to get the actual. Hold on, let me get the other side of this. And sorry, looks like it's going to put it here. And, to get the native orientation of a tablet device. It only shows about 1% here, but you have to realize that's part of a multi-threaded sample, so it actually ends up being about 4 to 5% of our overall main thread, depending upon the scenario. And the thing you really have to kind of take back from this is you can't, with the WinRT, trust that properties are just simple field fetches. They may very well have complicated behaviors behind them, and you absolutely need to use your resources here to understand what's actually going on here. In this particular case, display properties native orientation maps to registry queries. So we can easily cache and invalidate that when the orientation change property is fired, or the orientation change event is fired, but without being able to measure it, you really wouldn't have any idea that this function, which seems so innocuous, would be a problem. Also, specifically on the CPU side, for Surface RT in particular, you may see functions like RT-UDIV taking a significant amount of time. The Surface RT ARM processor doesn't feature an integer divide instruction. So you should try to make sure any of your hot data paths requiring division or mod, like hash tables, are built on power of 2. Another thing, you should not expect to get significant benefits out of just moving to Neon instructions. The Neon registers do not have any greater memory bandwidth than your general purpose registers. Memcopy, for example, under the covers does not use the Neon instruction sets, and it's actually doing the right thing. I checked. I didn't really believe it either. Neon instructions, however, can be extraordinarily useful to accelerate math and avoid register pollution. So another issue that we ran into during development was just severe performance drops. We found that as soon as people started interacting with the Surface, we would lose 4 to 5 frames. And none of our Visual Studio profiles were really showing us what was going on. So in this case, I think you need to upgrade a little bit and to try to get something that gives you a better sense of what the overall system's doing. So let's look at the Windows Performance Analyzer. If you're not familiar with Windows Performance Analyzer, it's available through the Windows Performance Toolkit and uses ETL logs at its basis. There are some great resources at MSDN for kind of understanding what it does. But it is just an extraordinary tool for giving you a holistic idea of what the system on the whole is actually doing. So in this case, let's go take a look at what the CPU is actually doing while we're playing our game. So in this case, we're going to see a timeline. And on here, we're going to be able to see that our game looks like right now it's doing pretty good. It's taking up about 50-something-odd% of the time. And that indicates we're doing OK as far as overall multi-core usage. But something kind of stands out here where we see DWM taking up a large amount of time. So let's dig a little bit deeper and try to find out what DWM is doing. So in this case, let's just filter DWM. And let's change over so that we're looking at just the table of data. And let's add call stacks in. So we just add stacks. Okay. Now we can just walk the stack down. Oh, let's make sure we load symbols. Might be helpful. and see the work that DWM is actually doing in this case. Again, you look at the weight column, and you'll just kind of follow that down level by level. So we see there's a partition thread. Not entirely sure what that is. Process frame. Process frame. Render. DWM is, oh, OK. Looks like DWM is doing a composition with our game. So knowing that DWM is doing a composition allows us to look a little bit more efficiently around MSDN and around the internet to get a better understanding of kind of what's going on. And what we found was that the pointer visualization settings are actually on by default. These pointer visualization settings are just little indicators that you kind of see on the thumbs or any other touch inputs that kind of just show you as you're moving around the screen as you swipe. DWM composes that on top of your game's runtime. This is horrendous for performance. You do not want to be falling into any DWM composition case. So definitely, you can use WPA to look at what DWM is doing, look at what its overall time is, and just absolutely make sure you're not compositing. Definitely, if you see a significant amount of time from DWM during your game's runtime, something bad's happening. And you should also make sure to disable both the contact feedback and the barrel button feedback on the pointer visualization settings. I have talked to some folks internally, and that should be updated in the default DirectX sample going forward. We also talked a little bit about GPU performance. And you can actually get quite a bit out of just using the Visual Studio graphics debugger. So I think one of the most straightforward things to look at is just kind of getting a sense for what your overdraw looks like, given how expensive that kind of is on these low-power GPU platforms. So that's just as simple as taking a capture. You just hit print screen, whatever you want to save out what everything's doing. You can see on the left here, we've got a list of all the API calls that occurred during that frame. And then we can just select a pixel, and it'll tell me exactly what calls went to go modify that pixel, which is great. So now we can see that we do a clear. OK. In this particular case, we're going to be drawing to all the different pixels on the screen. So a clear actually ends up being a 1.5 millisecond or millisecond no-op on the GPU. So we definitely want to look at getting rid of any of those clears as long as we're going to write to the whole thing. Please do make sure to use the discard view call to get that same benefit for any of the tile-based GPUs. Then we also probably want to look at and see if any of our other draw calls touch a lot of pixels. And we can actually get a fairly good sense of that just by kind of looking at the graphics pipeline stages down here and seeing what's actually getting drawn out to output merger. So in that case, it looks like it's going to be a large part of geometry. OK. Yeah, it's pretty straightforward. Just a little bit more geometry. And then what's this guy? Looks like we had a UI up. And it looks like, according to output merger, we actually touched every pixel on the screen. And here was the pixel shader output. This is pretty much one of the worst possible cases as far as bandwidth goes, because we're going to be drawing a full screen quad and blending the whole thing over. So definitely avoid anything that looks like a full screen pass and have your artist break those up into individual sections as best as possible. Just definitely don't put together any draw calls that touch a lot of pixels. In this particular case, you can also, from the graphic event lists, you can just use search to just get a good sense of the number of draw calls you're doing. You can cut and paste that over to Excel. What we found, at least for Surface RT, is about 400 draw calls with their associated state changes is about the maximum we can really expect from a dedicated render thread. You shouldn't really expect deferred context to help you on feature level 9 devices. OK. And then last, I wanted to go over a few different things you can do with GPU view. Of all of our tools, GPU view is probably the most intimidating. So let's just fire it up and then see if we can simplify things a little bit, because a lot of it's just trying to account for cases that are not necessarily as interesting for us on the performance side for this. So once you start it up, it's going to be probably a fairly large timeline. You're going to want to start zooming in to get an idea of what a couple frames of information look like. And then on the left here, you're going to see all the different processes that are in your system. So let's start at the top, though. Here's the GPU hardware queue. Here's what's actually executing on the hardware. This is the flip queue. This is really what's going on with DWM. DWM does all of your actual present information. So when you call present inside of your application, it's going to then schedule all that work in the GPU and then put a token over there that then gets pushed onto the flip queue to actually show that information to the user. So the data really moves throughout this system pretty significantly. But let's go down and let's go try to find our particular game here. Okay, now on this, what you're going to see here is a different timeline for each one of our threads. The numbers on each of these corresponds to the priority of that thread. The color is corresponding to which CPU this actually executed on. And what you're going to see up here is these are the GPU calls that we actually made. You'll pretty much see calls start off here in the context CPU queue. Then it will move up to the GPU hardware queue, and then you'll see it migrate down to the flip queue. So it's kind of an up and down sort of process. In this case, you see we're doing relatively low numbers of actual presents, but look at all these different hash marked present packets that are actually getting injected into the flip queue. So something bad's going on again, and yes, this is actually DWM. This is DWM again doing its composition. If you see any of this kind of a pattern, you don't want to see that anymore. So just make sure that you're seeing kind of regularly spaced interval of presents and not just this kind of mishmash that we're seeing on this. So this report's pretty muddied by just all the different presents that we're doing. So let's go and move to a somewhat cleaner profile that we had after we've addressed that composition. Okay. So this is another example of capture. I always like to turn on the vsync line so you can just kind of see and get a good sense for how we're matching up the times. There is quite a bit of overhead in capturing stack traces for ETL. So in this case, we're only presenting 1 out of every 3 frames. But what we do end up seeing here when we go down to our game is we're seeing these very, very large stacks. And we can kind of see again how present, again, which is this hash mark, move through the system. This present in this case actually ended up taking probably about 150 milliseconds to actually process. What this translates to is significant amount of control latency. So for our case, we put our thumbs down on the screen, and then we would lose 150, 200 milliseconds till you were actually able to interact with the device. So, I mean, GPU view is great at telling you're compositing and giving you a really good sense of the time difference between when you told something to visualize and when it actually was presented on screen. I don't know any other tool that can really give you that information. So in this case, the error we were running into was the maximum frame latency that's set on the DXGI device. The DXGI device maximum frame latency is actually set to 3 by default, which is exactly what we're running into here. You probably, for your game, want that to be 1 at most. Okay. In summary, though, your performance problems are pretty solvable as long as you use the right technologies, you set solid budgets, and you just can't be intimidated by the tools. And there are absolutely great resources out there. Halo Waypoint for all things Halo, of course. Maximum Performance talks last year, and I'm sure some great presentations this year around performance tips for Windows Store apps using DirectX and C++. He goes over GPU view in quite some depth. There's a series of blog articles written by Bruce Dawson from former Microsoft and now Valve around WPA and XPerf. Those are really great for just getting a foundation on how you can set up different types of analysis. And last, lighting material of Halo 3, if you've ever really wondered in depth the lengths people go through to try to get photorealism on current gen consoles. Okay. And I think that's pretty much it. I know we were looking to take questions. Turn you back on. Am I back on?
Hello? Hello? Okay, great. Yeah, at this point, so we wanted to, wow, we are exactly on target. We wanted to keep 15 minutes at the end in case anyone had any questions. If you do, please feel free to step to a mic so everybody can hear you. I don't see, oh, are they leaving or going for the mic? If not, thanks very much for coming. Hopefully you guys found it helpful. And Greg and I will be here for a couple of minutes. Oh, wait, there's one. All right.
So why didn't you implement multiplayer?
I'm sorry, I didn't hear. What was that?
Why did you implement multiplayer?
So yeah, that's a great question. So we had a pretty good challenge that we wanted to focus on, and that was making sure we nailed the base mechanics for the game. Without saying too much, I can say we do have plans to continue to support the title post-launch. So just keep an eye out for other stuff that could be coming. Yeah.
How is the performance on Windows phones?
So the question is, how is the performance on Windows phones? Without going into comparative metrics, we found the Windows Phone performance to work quite well out of the box. Really targeting Surface RT seemed to put us in a great position for also working well on Windows Phone.
Do you know the frame per second that it's having in Windows Phone? I mean, in average frame per seconds and tablets that you have a game?
I'm sorry, I didn't quite catch that.
I think
Frame per second?
frames per second on phone or
FPS?
Oh, yeah, on phone?
Yes, in phone and in tablet.
So for, again, Windows RT, we are very close to 30. Very close. And we spent a lot of time optimizing it out. For phone, I know we feel like, I think we're actually a pretty good solid 30 on phone. Yep. And for the Surface Pro, I think we're actually at 60.
Correct. Yeah, so and we still got to, obviously, so we're releasing mid-July, so we should be minimum 30 across the board, and in some cases higher by the time we launch. All right, looks like it's it. Hey guys, thanks very much. Hopefully you guys got some good little tidbits out of this. And again, feel free if you want to fire any questions off to Greg or myself, or just come on up and we'll answer what we can for you while we're here. Thanks very much. Well done.